Now, along with Galileo and Newton, another person who made incredible contributions to understanding planetary science was Kepler. Kepler was an excellent mathematician. Now, a question sometimes comes, well, what about Copernicus? Kepler and Galileo are the ones who kind of confirmed what Copernicus was saying, that the Earth isn't the center of the solar system, that it's better to think about the sun at the center of the solar system. So Kepler worked with an astronomer by the name of Tycho Brahe. And Tycho was an excellent astronomer. He could go out and take the numbers. But he wasn't as good of a mathematician as Kepler was. So he needed Kepler to do the mathematical work, and they're known as Kepler's law. And there's two of them. The orbit of each planet is an ellipse, with the sun at one focus. And each planet sweeps out equal areas in equal time. Then here's the mathematical form. The radius of one cubed over the period, or the time for one rotation squared, is equal to the radius of the other cubed over the time or the period of that planet squared. And you're going to see that it's really, really nice to work with. So let's see what an ellipse is. If we wanted to draw an ellipse, like let's say we had a piece of corrugated cardboard, we could put two thumbtacks and put a string between them. And if we had a pencil or a pen or a marker, you see how it's doing that? So imagine a marker at that point on the outside, the red point on the outside, we could trace an ellipse. So the way a circle has a center, an ellipse has two foci or focal points. And it turns out that we don't orbit the sun in a circle. We orbit the sun, and the orbit of every planet is an ellipse. And there is another focal point. And it turns out there's quite a bit of distance between those two focal points. And you know what's at that other focal point that I have set as X, that I've drawn as X on this picture? Nothing. It's just empty space. So we actually orbit the sun in an irregular, not a perfect circle, but an ellipse. Ellipse is kind of like an oval, and ellipse is like the mathematical definition of an oval. There is no mathematical definition for an oval. There is for an ellipse. Oval is just kind of a general term that we use. And each planet sweeps out equal areas in equal times. Now that one's a little harder to get our minds around. But what it really means is, when we're close to the sun, let's say this is 1 month, and I'm just making up a number. The Earth has traveled quite a distance in 1 month. Here's the sun. When the Earth is further away from the sun, if this were also a month, and like I said, I'm just making up, it could be 2 weeks, it doesn't matter. Notice that we've traveled much slower. So the travel time, the 1 month, is the same, but the Earth didn't go very far when it was well away from the sun. So the speed that we go around the sun changes. When we're close to the sun, we move much faster. When we're further from the sun, we move much slower. And I should say that when we're closer to the sun, it's not necessarily summer. In where we live in the northern hemisphere, it's actually winter when we're closer to the sun, and summer we're a little further away from the sun. When we're close to the sun, it is summer for the southern hemisphere, because remember, seasons are not caused by how close we are to the sun. They're caused by the tilt of the Earth. So I think this picture shows it really nicely. Notice how the planet slows down when it's far, far from the sun. But as it gets closer to the sun, it speeds up. So it slows down, slows down, slows down, slows down. And then as it's coming to the sun, coming closer to the sun, coming closer to the sun, it's picking up. It's almost like the whip or the whipper ride that they have at different amusement parks. So there's two equations we can consider. One is for one satellite, and we'll see that in another video. But today we just want to worry about Kepler's law, and let's just allow and compare between two satellites. what's really nice and what you're going to see is that sometimes we can get away with, we don't have to do all the math. We don't have to get everything into seconds all the time. So Mars is further away from the sun. Here's the sun, and here's the Earth. And here's good old Mars way out there. Mars. So the Earth takes 1 year to go around the sun. Mars takes 1.88 years. And we know the distance is for us to the sun is times 10 to the 8th kilometers. So what Kepler figures out is if he can do some measurements just by looking through telescopes, and he worked off Brahe's experiments and data, he can get some really neat information. So instead of 1 here, let's do radius of the Earth, the distance to the sun, over the time for the Earth squared, is the radius, the distance to Mars cubed, over the time to Mars, time for Mars, the period, squared. So let's see how this is going to work. The Earth is that far, that many kilometers to the sun. We're going to leave it in kilometers. I know it's shocking. Why didn't we go to meters? We don't need to. It's just now our answer will come out in kilometers. Here's where life's going to get really easy. We're going to not even go to seconds. We're going to just use 1 year squared. And for Mars, we're going to use 1.88 years squared. We can do this. I should say they both have to be in the same unit. This can't be in years and this in days, or this can't be in years and this in seconds. They have to both be in years. So the radius of Mars cubed, we're going to cross multiply. And luckily 1 squared down there is going to be 1. So this is going to be a really big number because I'm going to have to cube this one and square this one. And I'll have to figure out what that is on my calculator here because I don't know it off the top of my head, for shame. So the radius of Mars cubed is this big, big number times 10 to the 25th. That'll be kilometers cubed. So what we have to do is to take a cube root on our calculator. So let's see where I'm going to put that. You might have a button that says X, like that, where you would enter 3, and then X, like this, and then the big number. Some calculators will have a cube button. That's great. Or what I can do, and this is what I like to do, I can raise it, oops, not an A, it's a caret sign, raised to the 1/3. And the distance to Mars is 2.28 times 10 to the 8th kilometers. So not quite twice as far away as what the Earth is from the sun.